Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 34 on volume and dimension.
We've computed the areas of two-dimensional shapes and the volumes of three-dimensional shapes. What do you think comes next? The fourth dimension? The fifth dimension? In this lesson, we're going to do them all at once.
We begin our lesson with that timeless question. What is the fourth dimension? Well, that sounds kind of spooky. We're going to jack it up a level and answer the question, what is the nth dimension? But we're going to start at the beginning. Let's say n equals 1. What is that? Well, that's simply the real number line that you all know and love. We could coordinatize it by some variable, x. When we move up to the second dimension, well, now we have two variables to state where we are on the coordinate plane. Call it x and y. Three dimensions is a little bit harder to draw, but no less difficult to understand. We have x, y, and z. But now, when we get to the fourth dimension, it's a little difficult to draw pictures. We can, however, simply add another coordinate. You might be tempted to use t for time or some other variable name, but why don't we just use subscripts? x1, x2, x3, x4. The reason for this being that when we move to the nth dimension, well, for large values of n, we don't have enough letters, but we do have enough subscripts. Now, drawing pictures in the nth dimension is hard. Therefore, we're going to proceed by exploring through volumes and shapes. Three simple shapes in particular: cubes, simplices, which are analogs of triangles or pyramids, and balls. Now, what do we mean when we say volume in high dimensions? Well, let's take a moment and think about that. As dimension of an object goes from 0 to n, we know what three-dimensional volume means. That's simply volume. But we also know what two-dimensional volume means. That is area. What is one-dimensional volume? Well, that is really length. Okay, you've got those three down. What is zero-dimensional volume? Well, a zero-dimensional object is simply a collection of points. How many points? That is the volume. Zero-dimensional volume is counting. And now, with these in place, we can move to n-dimensional volume, which we will call hypervolume if we're feeling epic, or we might just simply call n-volume. That will work. Let's build our intuition for n-dimensional volume by looking at an n-dimensional cube. This is going to be a cube where all of the sides have unit length. So in dimension 3, it's the familiar object. What is a two-dimensional cube? It's simply a square with side lengths 1. What is a one-dimensional cube? Well, it's got to be some interval, an interval of length 1. What's a zero-dimensional cube? It's a zero-dimensional set whose volume, or count, is equal to 1. It's just a simple point. And from that, we can extrapolate to higher dimensional cubes. But at this point, pictures fail, and we need to translate to equations. Therefore, we'll define the unit n-dimensional cube as those points in n-dimensional space whose coordinates, x sub I, satisfy the inequalities x sub I bigger than or equal to 0 and less than or equal to 1 for all I. Now, how do you visualize that? Well, it's hard to do with your eyes, but you can do it with your hands. If you think of each coordinate as an independent parameter, then it is remarkably similar to what happens when you slide an equalizer or slider bars up and down. Perhaps you've played with something like this on a sound system. Each of those slider bars is like a coordinate in the n-dimensional cube, where n is the number of slider bars. Each can go up or down, independent of the other, until you hit the boundary, where it has to stop. Now, with that in mind, let's take a look at volumes. As we consider what happens in each dimension, how do we get from one cube to the next? At each stage, what we're doing is taking the lower dimensional cube and then crossing it with an interval, making a one-parameter family of such objects. Now, in every case, the volume is 1. We're used to that in area, length times width, or in 3D volume, length times width times height. In each case, it's 1 times 1 times 1. In fact, this is really the basis for how you should think about n-dimensional volume. The surface area, well, that's a little bit harder to wrap your brain around, but we want to look at the boundary of the cube and say how much n minus 1 dimensional volume is there. So if we take a one-dimensional interval and say, what's the zero-dimensional volume of the boundary? That is, how many points on the boundary? Well, simply 2. Surface area for a two-dimensional object is what we used to call perimeter. And in the case of a square, the perimeter is 4. There are 4 unit edges. Of course, the surface area for a three-dimensional cube is what? Well, you look at each of the 6 faces and compute its unit area. Adding together gives 6. Now, in general, one could argue correctly that the surface area of the n-dimensional cube is in fact 2n, the number of boundary faces that you have. And that pattern works all the way down, even to dimension 0. The diagonal of a cube is the distance between opposite corners. We know from Pythagoras what that is for a two-dimensional cube. That's square root of 2. What about for a three-dimensional cube? Well, we would have to apply the Pythagorean theorem twice to obtain the square root of 3 as the length of this long diagonal between opposite corners. If we continue inductively, we can show that the diagonal of the n-dimensional cube has length square root of n. That's a little crazy, because for large values of n, you can have a very, very small unit cube such that the opposite corners are very, very far apart. That's a little strange. But this pattern continues down, even to dimensions 1 and 0. Lastly, if we count the number of corners in an n-dimensional cube, we see for a square, there's 4. For a cube, there is 8. And in general, it's not hard to show that there are 2 to the n corners. Let's move on to a different shape, one that requires some calculus to understand. This is the simplex. This is an n-dimensional generalization of a triangle or a pyramid. The unit simplex is defined algebraically as a subset of the unit cube that satisfies an additional constraint, this being that the sum of the coordinates is less than or equal to 1. Well, what does that mean in terms of our slider bar analogy? This means that you can take any of the individual bars and slide it all the way up to 1. However, you can't do this independently. If you want to move the other slider bars up, you have to do so in a way that the sum of the values does not exceed the threshold of 1. That means that this is a highly constrained set. It's not a large subset of the n-dimensional cube. It feels much smaller. We expect to see that reflected in the volume. Let's see how that works. First, let's explore a few properties, and then we'll compute the n-dimensional volume. The number of corners of an n-dimensional simplex is much less than that of a cube. The n-dimensional simplex has n plus 1 corners. What is the volume? Well, we know for a single simplex it's just a point. The number of points is 1. We know for a one-dimensional simplex, since it's the same as a one-dimensional cube, we just get a length of 1. Now, a triangle, as we all know, gives us area 1/2. When we look at a three-dimensional simplex, it's a cone over that triangle. We know the volume of a cone is going to be 1/3. The height, 1, times the area of the base, 1/2. Now, we start to see a little bit of a pattern here. What if I told you that the four-dimensional simplex had four-dimensional volume equal to 1/24? That's true. And knowing that, you would be convinced of the pattern, namely that the volume of the n-dimensional simplex, v sub n, must be 1 over n factorial. Now that's a good guess. Let's see if we can show it. Our strategy for computing volumes of the n-dimensional simplices is the same as that of a cone. We're going to slice in a direction parallel to the base. And what we're going to see is that when we slice an n+1 dimensional simplex, what we'll get is an n-dimensional simplex whose size is rescaled by a factor of x in each coordinate, where x is the distance to the top of the simplex. So, for a one-dimensional simplex, the appropriate volume element of the slice is nothing more than dx. In a two-dimensional simplex, the appropriate area element is what? It's simply x dx. In the three-dimensional case, well, we've done this before. This is going to be 1/2 x times x dx. And in general, the difficult step is to argue that the volume element for the n+1 simplex is the volume of the base n simplex, v sub n, times x to the n, since we're rescaling each coordinate by a factor of x. But once we have that, and then multiplying by the thickness, dx, we can compute this n+1 dimensional volume as the integral of the volume form. That is the integral of v sub n times x to the n dx, integrating as x goes from 0 to 1. This is a trivial integral since v sub n is a constant. We obtain x to the n+1 over n+1 evaluated from 0 to 1. That gives us v sub n over n+1. And so we can write down all of these volumes by induction and argue that v sub n is in fact 1 over n factorial. That's a nice application of simple integration. Let's move on to an n-dimensional ball of radius 1. These are a little difficult to draw. In 2D, this is simply a disk of radius 1. In 1D, it's a disk of radius 1. Well, it's really an interval of length 2. And in 1D, it is, again, a simple point. Higher dimensional balls are not so easy to draw. Now, how do we define it rigorously? The unit ball is defined as those set of points with coordinates x sub I between -1 and +1, satisfying the additional constraint that the sum of the squares of the coordinates is also less than or equal to 1. This is what we're used to in 2D when we say x squared plus y squared less than or equal to 1. This is simply the generalization of that. Now, in terms of a slider bar analogy, now all of the individual bars can go from -1 to 1. Each can go to the very top or the very bottom. But in between, well, you have some freedom to move the individual sliders up and down, but you can't move them all past a certain point where the sum of the squares is less than or equal to 1. Nevertheless, it feels like there's a lot of room inside of there to move around. How do we compute the volume? Well, again, for a radius 1 ball in dimension n, what is the volume going to be? In dimension 0, there's a single point, volume 1. In dimension 1, this interval has length 2. In dimension 2, well, we know the formula, pi r squared. In this case, r equals 1. In dimension 3, volume is 4/3 pi. Moving up to dimension n, well, what are we going to do here? Let's call that volume of the unit ball v sub n. And to determine what that is, let's consider what happens when the radius is not 1, but r. In this case, the length of the one-dimensional ball is 2 times r. The area of the two-dimensional ball is pi r squared. The volume, 4/3 pi r cubed. In general, having a ball of radius r in dimension n is going to give you the volume of the unit ball times r to the nth power. And that's going to be helpful for us, as we'll see. The surface area is what? Well, in the one-dimensional case, it's 2. In the two-dimensional case, we're looking at the circumference. That's 2 pi r. In the three-dimensional case, the surface area of the ball is 4 pi r squared. Do you see a pattern? Yes, it's related to the derivative. In fact, it's going to be, in the n-dimensional case, n times v sub n times r to the n minus 1. You'll be able to prove that result in multivariable calculus. What's the diameter? Well, in all cases, it's equal to 2 times r, or in the unit case, 2. Now, let's see if we can figure out what this n-dimensional volume of the unit ball, v sub n, is. Well, we're not going to be able to prove it in here. We'll do it in the bonus lesson. Suffice to say that with some work, one can show that the volume of the n-dimensional ball of radius 1 is, when n is an even number, let's say 2 times k, then the volume is pi to the k over k factorial. When n is odd, that is 2k plus 1, then the volume is pi to the k factorial 2 to the n over n factorial. Whew, that's kind of complicated. We'll show you how to get this in the bonus material. But for now, the question I want you to consider is, what happens to the volume of the unit ball as the dimension increases? Well, let's see. N, and thus k, are getting bigger and bigger and bigger. But there's a factorial in the denominator. What happens then? This means that the volume does not get bigger as the dimension increases. In fact, the volume goes to 0 as dimension increases. And it goes to 0 rapidly, since factorials beat powers. This is cause for some alarm, for some puzzlement. What does this mean? Well, let's think in terms of the difference between a ball and a cube in dimension n. Let's say we have them fight. Who wins? Well, in low dimensions, the ball of radius 1 definitely has more volume or area than the cube of side length 1. This is true in 2D. It's even true in 3D. But it is not true in all dimensions because of those corners in the cube. Those corners eventually stick out from the ball, even when the two are concentric. And all of the volume inside the n-dimensional cube lives in those corners. That's why cubes beat balls.
This lesson was neither short nor simple. It may take a little time for things to sink in. Don't worry. You're not going to be asked any questions about hypervolumes of balls on the final exam for this course. And in our next lesson, we're going to return to the more familiar low-dimensional world. But step back for a moment. Think about what you've done. We have, with rational thought and calculus, measured objects that you cannot see, smell, taste, touch, or experience with your senses. That's not a bad day's work.